Welcome to this coding walkthrough. In this session, we'll explore the problem diet plan performance and analyze its solution. We'll break down the approaches step by step to help you gain a deeper understanding. Let's get started. In this problem, we are evaluating the performance of a diet plan by analyzing calorie intake over a period of time. Each day, you record the number of calories consumed, and you aim to stay within a daily calorie limit. To assess how well you're doing, you'll calculate a performance score based on a sliding window of consecutive days. Specifically, for each group of k consecutive days, you calculate the total calorie intake. If this total is less than a given lower threshold, your score decreases by 1. If the total exceeds an upper threshold, your score increases by 1. Otherwise, the score remains unchanged. The goal is to compute the total performance score across all possible windows of k days. Now, let's look at the output format and an example to understand this better. The output for the problem is a single integer representing the total performance score. For instance, consider the first example where the calorie intake for each day is 1, 2, 3, 4, 5, the window size k is 1, and both the lower and upper thresholds are set to 3. Here, since k is 1, we evaluate each day's calorie intake individually. Depending on whether the calorie value is less than, greater than, or equal to the threshold, the score is updated accordingly. We'll calculate the total score over all days in this example. Breaking this example down, we see how the score is determined. On day 1, the calorie intake is 1, which is less than the lower threshold of 3, so the score decreases by 1. On day 2, the intake is 2, which is still less than 3, so the score decreases by another 1. On day 3, the intake is equal to 3, so the score remains unchanged. On days 4 and 5, the calorie intakes are 4 and 5 respectively, both of which are greater than 3, so the score increases by 1 for each of these days. Adding these changes together, the total score is -1 plus -1 plus 0 plus 1 plus 1, which results in a final score of 0. This demonstrates how the scoring system works for a single-day window. Let's consider another example to understand how the score changes with a window size larger than 1. Here, the calorie intake is 3, 2, the window size k is 2, and the thresholds are lower equals 0 and upper equals 1. Since k is 2, we only have one window to evaluate, 3, 2. The total calorie intake for this window is 3 plus 2, which equals 5. Because 5 is greater than the upper threshold of 1, the score for this window increases by 1. Since there's only one window, the total performance score is 1. Now, let's look at a third example with a longer calorie intake list and a larger window size. Here, the calorie intake is 6, 5, 0, 0, the window size k is 2, and the thresholds are lower equals 1 and upper equals 5. With k equals 2, we evaluate three windows, 6, 5, 5, 0, and 0, 0. For the first window, 6, 5, the total is 11, which is greater than the upper threshold, so the score increases by 1. For the second window, 5, 0, the total is exactly 5, which matches the upper threshold, so the score remains unchanged. For the third window, 0, 0, the total is 0, which is less than the lower threshold, so the score decreases by 1. Adding these together, the final score is 1 plus 0 to 1, resulting in a total score of 0. Finally, the constraints and edge cases are important to consider, as they ensure that your solution can handle large inputs efficiently and account for different patterns in the data, such as single-day windows, widely separated thresholds, or uniform calorie values. To solve this problem, we can start by considering a brute force approach. The main idea here is to calculate the sum of calories consumed over every possible subarray of length k and then evaluate this sum against the given thresholds, lower and upper. To do this, we iterate through all potential starting indices of these subarrays. For each starting index, we compute the sum of the k consecutive elements from scratch and then adjust the score based on whether this sum falls below lower, exceeds upper, or lies in between. While this method is straightforward and easy to implement, it is computationally expensive. Specifically, for each of the n starting indices, we compute a sum involving k elements, leading to a time complexity of n*k. This makes the brute force approach impractical for larger arrays due to the repetitive nature of the summation, which introduces significant inefficiency. To address the inefficiency of the brute force method, we can turn to the sliding window approach. This technique significantly optimizes the process by reusing previously computed information. Instead of recalculating the sum from scratch for each subarray, we simply adjust the sum by subtracting the element that is sliding out of the window and adding the element that is sliding in. This way, we can maintain the sum in constant time as the window moves. Initially, we calculate the sum of the first k elements, and then as the window slides across the array, we continuously update the sum and evaluate it against the thresholds to modify the score. This results in a linear time complexity of O(n), which is much more efficient. The sliding window technique is not only optimal but also simple to implement, provided we carefully handle edge cases like empty arrays or scenarios where k exceeds the array size. By choosing this approach, we strike a balance between efficiency and clarity, making it well suited for solving this problem at scale. Additionally, this method highlights the importance of recognizing overlapping subproblems, a key concept in optimizing array-based computations. To tackle the diet plan performance problem, the first step is to clearly understand the task. We are given an array called calories with n elements, an integer k representing the size of the subarray, and two thresholds, lower and upper. The objective is to calculate a score by evaluating the sum of calories for every subarray of size k. If the sum exceeds the upper threshold, we add 1 to the score. If the sum is below the lower threshold, we subtract 1 from the score. If the sum falls between lower and upper, inclusive, the score remains unchanged. To begin solving this, a brute force approach can be employed. This involves iterating through every possible subarray of size k. For each subarray, we calculate its sum, compare it to the thresholds, and then update the score accordingly. While this approach is straightforward, it can become inefficient as the size of the input grows, a limitation we will address later. The brute force method can be broken down into detailed steps. First, initialize the score to 0 as it will store the final result. Then, iterate through the array from the starting index I equals 0 up to n(k), which is the last valid index for subarrays of size k. For each starting index I, extract the subarray of size k using calories, I plus k, and calculate its sum. This sum, referred to as current_sum, is then compared to the lower and upper thresholds. If the current_sum exceeds the upper threshold, increment the score by 1. If the current_sum is less than the lower threshold, decrement the score by 1. If the sum is within the thresholds, no changes are made to the score. Once all subarrays have been processed, the final score is returned. While easy to implement, this method is computationally expensive due to the repeated sum calculations for overlapping subarrays. To optimize the brute force approach, we can use the sliding window technique. Instead of recalculating the sum for every subarray from scratch, we maintain a rolling sum that updates as the window shifts. This eliminates redundant computations and reduces the time complexity significantly. The process starts by calculating the sum of the first subarray of size k, which we call current_sum. Initialize the score to 0. Then, iterate through the array starting from index k to the end. For each iteration, compare current_sum to the thresholds and update the score as needed. Next, slide the window forward by subtracting the first element that is leaving the window and adding the new element that is entering the window. This allows the current_sum to be updated in constant time. After processing all subarrays, the final score is returned. This approach improves the time complexity from O(n*k) to O(n), making it far more efficient. The sliding window optimization provides key insights into the problem. The brute force approach, while simple, recalculates sums for overlapping subarrays, leading to unnecessary computations. The sliding window technique addresses this inefficiency by maintaining a rolling sum, which updates dynamically as the window shifts. This eliminates redundant calculations and makes the algorithm more scalable for larger inputs. Some edge cases to consider include scenarios where the array length n is less than k, in which case no valid subarrays exist, and the function should return 0. If k is equal to n, the entire array forms a single subarray, and we simply compute its sum to determine the score. Lastly, if all elements in the array are the same, the score depends entirely on whether this constant sum lies above, below, or within the thresholds. To implement the solution, the primary data structure is the input array, calories. Accessing elements in an array is efficient, with a time complexity of O(1). The sliding window technique leverages this efficiency by maintaining a rolling sum that updates with each shift of the window. Importantly, no additional data structures are required, keeping the space complexity at O(1). When analyzing the computational complexity, the brute force approach has a time complexity of O(n*k), due to the nested loops required to calculate sums for all subarrays. In contrast, the sliding window technique processes each element of the array only once, resulting in a time complexity of O(n). Both approaches have a space complexity of O(1), as they do not require extra storage beyond the input array and a few variables. Handling edge cases is crucial to ensure the algorithm is robust. If the array length n is less than the subarray size k, no valid subarrays can be formed, so the function should return 0. When the thresholds lower and upper are set to extreme values, all subarray sums may fall into the same scoring category, meaning the score will be consistently positive, negative, or 0. For single-element subarrays, where k equals 1, the problem reduces to comparing each individual element to the thresholds. These considerations ensure the algorithm accounts for all possible scenarios, providing accurate results across diverse inputs. This implementation solves the diet plan performance problem using a sliding window approach, which ensures efficiency. The function starts by initializing the total score to 0. It calculates the sum of the first subarray, or window, of size k using Python's sum function, which is efficient for this initial calculation. This sum is then compared against the upper and lower thresholds to adjust the score, adding 1 if the sum exceeds upper, subtracting 1 if below lower, and no change if within the range. The key optimization comes with the sliding window technique. Instead of recalculating the sum for every subarray from scratch, which would be computationally expensive, it updates the sum by subtracting the element that is sliding out of the window and adding the new element coming into the window. This reduces the complexity of updating the sum to O(1) per step. For each new window sum, the code again checks it against the thresholds to adjust the score accordingly. This process is repeated for all possible subarrays of size k by iterating through the array. The function finally returns the computed score after evaluating all windows. This algorithm has a time complexity of O(n), where n is the size of the calories array, due to the single pass required to slide the window across the array. The space complexity is O(1), since no additional data structures are used beyond scalar variables. This makes the solution efficient and well suited for the problem constraints. Here, we are implementing the solution for the diet plan performance problem in Java. We start by defining the method diet plan performance, which takes in an array of calories, an integer k for the window size, and two thresholds, lower and upper. First, we calculate the total number of elements in the calories array and initialize the score variable to 0. This will be our running total to track the diet performance. Next, we calculate the sum of the first window of size k by iterating through the first k elements of the array and adding them to the window sum variable. Once we have the sum of this initial window, we evaluate its performance. If the sum exceeds the upper threshold, we increment the score by 1. If it falls below the lower threshold, we decrement the score by 1. After processing the first window, we then prepare to slide the window across the rest of the array, updating the window sum dynamically by subtracting the element that is leaving the window and adding the element that is entering it. For each new window, we evaluate its performance just like we did for the first one. If the updated window sum is greater than the upper threshold, we increase the score by 1. If it's less than the lower threshold, we decrease the score by 1. This process continues until we have evaluated all possible windows of size k in the array. Finally, once all windows have been processed and the score has been updated accordingly, we return the score as the output of the method. This approach efficiently slides the window across the array, ensuring that we only perform constant time updates for each new window, resulting in an overall time complexity of O(n). This makes the solution both optimal and easy to understand. To begin understanding the solution, let's walk through the first example. We are given an array of calories, 1, 2, 3, 4, 5, a window size k equals 3, and thresholds lower equals 6 and upper equals 10. First, we initialize the length of the calories array, n equals 5, and set the initial score to 0. Then, we calculate the sum of the first window, which is the sum of the first three elements. 1 plus 2 plus 3 is equal to 6. This value, 6, is equal to the lower threshold. Since the sum is neither below the lower threshold nor above the upper threshold, the score remains unchanged at 0 at this point. Next, we slide the window one position to the right, starting at index 3. Removing the first element from the window and adding the next gives a new window sum of 6 minus 1 plus 4 is equal to 9. This sum is between the lower and upper thresholds, so the score remains 0. Then, we slide the window again to include the next set of elements, updating the window sum to 9 minus 2 plus 5 is equal to 12. Now, the window sum of 12 exceeds the upper threshold of 10. This means we need to increment the score by 1, resulting in a final score of 1 for this example. The key takeaway here is how the score changes based on the relationship between the window sum and the thresholds. The window starts below the upper threshold but eventually exceeds it, which leads to a positive adjustment in the score. Let's move to the next example. Here, the calories array is 1, 1, 1, 1, 1, with k equals 2, lower equals 5, and upper equals 7. This scenario is designed to show how the score behaves when all windows fall below the lower threshold. In this second example, we start by initializing n equals 5 and the score at 0. The first window sum is calculated as the sum of the first two elements. 1 plus 1 is equal to 2. Since 2 is less than the lower threshold of 5, we decrement the score by 1, making the score minus 1. Next, we slide the window to the right by 1 position. The new window sum is updated as 2 minus 1 plus 1 is equal to 2, which is still below the lower threshold. As a result, we decrement the score again, bringing it to minus 2. This pattern continues as we slide the window further. The window sum remains 2 after each update, and since it is consistently below the lower threshold, the score decreases by 1 each time. By the end of the array, after sliding the window to cover all possible positions, the score reaches minus 4. This example illustrates how the score can decrease when all sliding windows fail to meet the lower threshold. Every window sum contributes to a negative adjustment in the score. Now, let's consider a mixed case where the window sum transitions across both thresholds. The input is calories equals 6, 5, 0, 0, 10, 15, with k equals 3, lower equals 10, and upper equals 20. This will help us see how the score is affected by window sums that span the entire range of possibilities. For the third example, we start with n equals 6 and initialize the score at 0. The first window sum is calculated as the sum of the first three elements. 6 plus 5 plus 0 is equal to 11. This value falls between the lower and upper thresholds, so the score remains unchanged at 0. Sliding the window to the next position, we update the sum by removing the first element and adding the next. 11 minus 6 plus 0 is equal to 5. Since 5 is less than the lower threshold, we decrement the score by 1, resulting in a score of minus 1. Moving the window again, we update the sum to 5 minus 5 plus 10 is equal to 10. This time, the window sum is exactly equal to the lower threshold, so the score remains minus 1. Finally, sliding the window to include the last set of elements, the sum becomes 10 minus 0 plus 15 is equal to 25. Now, the window sum exceeds the upper threshold, so we increment the score by 1, bringing it back to 0. The final score for this example is 0. This mixed case highlights the importance of tracking the transitions of the window sum across the thresholds. We observe how it is possible for the score to remain stable when the sum falls within the bounds, decrease when the sum is below the lower threshold, and increase when it exceeds the upper threshold. Additionally, situations where the sum is exactly equal to the thresholds result in no adjustment to the score. These examples collectively demonstrate how the sliding window technique efficiently evaluates the diet plan performance under varying conditions. Here, we begin analyzing the time complexity of our solution. First, we look at the initialization and the computation of the first window's sum. This step involves summing up the first k elements of the calories array using the built-in sum function. Since this operation iterates through exactly k elements, it has a time complexity of O(k). Next, we consider the sliding window updates. In this part of the code, a loop runs from index k to n, where n represents the length of the calories array. This means the loop executes n, k iterations in total. During each iteration, the window underscore sum is updated by subtracting the outgoing element and adding the incoming element. Both of these operations are constant time, or O(1). Therefore, the cumulative time complexity for all sliding window updates is O(n)k). Now, let's focus on the time complexity of the score evaluation step. For each window of size k, the program checks if the current window underscore sum exceeds the upper threshold, falls below the lower threshold, or lies in between. Each of these comparisons is a constant time operation, or O(1), and they occur once per iteration of the sliding window loop. Since the loop runs n(k) times, the total time spent on score evaluations is O(n)k). Combining all these steps, we see that the first window computation takes O(k), and the sliding window updates along with score evaluations together take O(n)k). Adding these terms gives a total time complexity of O(k) plus n(k), which simplifies to O(n). This linear time complexity ensures that the solution is efficient, even for large input sizes. Turning to space complexity, the solution is highly efficient in its use of memory. The program primarily uses a few integer variables, such as n, score, and window underscore sum. These variables require a fixed amount of memory, regardless of the size of the input array calories. Additionally, the input array calories itself is not copied or modified in a way that would increase memory usage. Finally, the solution does not rely on any auxiliary data structures like stacks, queues, or additional arrays that might grow with the size of the input. This absence of additional memory allocation means that the space complexity of the solution is O(1), as it remains constant no matter how large the input becomes. Let's compare this optimized approach to a potential naive solution. In a brute force approach, one would calculate the sum for every possible window of size k within the calories array. For each of these windows, summing the k elements would take O(k) time, and since there are approximately n(k plus 1) windows, the total time complexity would be O(k*(n)k plus 1). This simplifies to O(k*(n) in the worst case, which is significantly more computationally expensive. In contrast, the sliding window technique avoids redundant calculations by updating the sum in constant time for each window. This optimization reduces the time complexity to O(n), making it far more efficient, particularly for large values of n and k. Furthermore, the time and space complexities are consistent across all scenarios, best, average, and worst cases, since the program processes the entire array in a single pass. This means we achieve O(n) time and O(1) space complexity uniformly. To solidify this understanding, let's consider the mathematical proof for the big O time complexity. The initial computation of the sum for the first window is O(k), while the sliding window operations collectively require O(n)k). When we add these two terms, O(k) plus O(n)k, the result simplifies to O(n), as the dominant term is linear in n. On the other hand, the space complexity remains O(1), because there is no additional memory allocation based on the size of the input. This optimal time complexity of O(n) and space complexity of O(1) highlights the efficiency of the sliding window technique, making it a superior choice compared to the naive approach. With this, we can confidently conclude that the solution is both time and space efficient, making it well suited for large-scale inputs. When tackling this problem, there are a few common mistakes to watch out for. First, incorrect sliding window implementation is a frequent pitfall. This happens when we forget to adjust the window correctly, such as not subtracting the element that exits the window. This oversight leads to inaccurate sums, which will directly affect the correctness of the results. Another issue is failing to account for edge cases. For example, if the array length is smaller than the window size k, or if k is 0, these scenarios can cause runtime errors or undefined behavior. Additionally, relying on a brute force approach instead of an optimized solution is inefficient. Calculating the sum of every possible subarray using nested loops results in a time complexity of O(n squared, which is impractical for larger input sizes. Lastly, off-by-one errors are another common source of bugs. For instance, using I plus k instead of I plus k1 to determine the end of the sliding window can lead to missing elements or going out of bounds. Carefully addressing these issues is essential for a correct and efficient solution. Another mistake to be cautious about is misunderstanding how to compare values against the thresholds. For instance, confusing the lower and upper bounds, or using inclusive comparisons like equals when strict inequalities are required, can cause the scoring logic to fail. Beyond mistakes, there are a few key insights to keep in mind for interviews. This problem exemplifies the sliding window pattern, which is a highly valued technique in technical interviews. Recognizing when to use a sliding window approach is an important skill. It's also useful to discuss the trade-offs between brute force and optimized solutions, as interviewers often value candidates who can analyze and articulate these differences. Additionally, demonstrating awareness of edge cases, such as empty arrays, k being larger than the array length, or extreme values for the thresholds, shows strong problem-solving skills. Finally, you should be prepared to explain the time complexity of your solution. For example, discussing why your approach achieves O(n) complexity and how this improves upon the O(n)² brute force method can set you apart as a candidate. This problem also connects to several related problems on LeetCode, which can help deepen your understanding of similar techniques. For instance, LeetCode 209, minimum size subarray sum, also uses a sliding window approach to find the smallest subarray meeting a certain condition. Similarly, LeetCode 643, maximum average subarray I, involves calculating subarray sums but focuses on finding the subarray with the maximum average. Another related problem is LeetCode 713, subarray product less than k, which explores subarray products instead of sums. Lastly, LeetCode 424, longest repeating character replacement, expands on sliding windows in the context of string manipulation. Beyond related problems, it's worth considering alternative approaches and their trade-offs. While the brute force method has a time complexity of O(n)², it can be acceptable for very small input sizes or when code clarity is prioritized over efficiency. On the other hand, the sliding window technique is far more efficient with a time complexity of O(n), although it requires careful implementation to avoid common pitfalls like indexing errors. Another alternative approach is using prefix sums, which also achieves a time complexity of O(n). This method involves pre-computing an array of cumulative sums, making it easier to calculate the sum of any subarray in constant time. However, it comes with the trade-off of requiring additional space for the prefix sum array. Finally, if the problem involves dynamic ranges or multiple subarray sum queries, a binary search approach may be applicable. This method has a time complexity of O(n) log n, and can be useful in scenarios where efficient querying is more important than the one-time setup cost. Each of these approaches has its strengths and weaknesses, and the best choice depends on the specific problem constraints and requirements. By understanding these variations and trade-offs, you'll be better equipped to select the most suitable solution for different scenarios. Great work! To wrap up, we covered the problem diet plan performance, breaking down key approaches and highlighting important concepts like sliding windows for optimizing array problems. Keep practicing and stay curious. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!